When we're working with oxidation and reduction reactions, one of the really important skills is to be able to look at any element and assign an oxidation number to that element. Sometimes that's a pretty easy thing to do, sometimes it's a little trickier, but I was told a method where you kind of use algebra to figure this out, and we're going to look at that method right now. Now, some oxidation numbers are obvious. If you have an element, we're going to say that the oxidation number of any element is 0. So the oxidation number of zinc would be 0 in zinc. If I had a chlorine molecule, each chlorine atom would be assigned an oxidation number of 0. If you have some sort of an ion, so let's say we get to the zinc ion, then the oxidation number of that ion is +2. So whatever the charge is on the ion, that becomes the oxidation number. When you get to a compound, then we can say, well, some of the elements in that compound have definite oxidation numbers. For example, fluorine. In its compounds, fluorine is always -1. Always -1 in its compounds. Now, it could be an element. We can have fluorine like that, and then that would have an oxidation number of 0. But in its compounds, let's say lithium fluoride, then the fluoride would always be -1. Other ones that are always true are the alkali metals. So the alkali metals in their compounds are always +1. And the second family, the alkaline earth metals, those are always +2. So these are always +1, these are always +2. Okay, and aluminum is always +3. Now there are a couple of them that are usually, okay, so oxygen in its compounds is almost always -2. Peroxide is a counterexample. And hydrogen in its compounds, if it's with a metal, then it has to be -1. But in its compounds, it's almost always +1. I mean, it's just normal compounds we would see. Well, let's go back and look at these examples. So if I had H2SO4 as my example, and we say, well, what is the oxidation number of sulfur? So we can just say, well, let's let X be the oxidation number of sulfur. And what do we have? We have 2 hydrogens, so it would be 2 times +1, plus sulfur, which is X, plus 4 times -2, because oxygen in its compounds is almost always -2. And since there is no charge on this H2SO4, then we say it's all going to add up to 0. So we can just now would solve our algebra problem. So 2 plus X plus -8. And you can play with that a little bit and find out that X equals 6. So the oxidation number of sulfur in H2SO4 is +6. Now it doesn't always have to be +6. So here's another example. And this is the sulfite ion. And we can see here we're going to say let that be X. And we have 3 oxygens, so that's 3 times -2. And since the ion has a charge of -2, then all of our oxidation numbers add up to -2 in this case. So for sulfuric acid, everything added up to 0, and in sulfite, everything's going to add up to -2. So X plus -6 equals -2, so therefore X, this oxidation number of sulfur in sulfite, in this case is only +4. So sulfite could be +4, sulfur in sulfite is +4, sulfur in sulfate, or H2SO4, is +6. Now, sometimes it's a little bit trickier, especially this one here, ammonium nitrate. You might think, well, let's just put this together to say N2H4O3, and then we'd have 2 times X plus 4 times +1 plus 3 times -2 equals 0, because this has 0 charge, and that's going to give us the wrong answer. We have to do this as 2 separate ions, because it turns out nitrogen is different in the 2 different, surrounded by different ions, and has different oxidation states. So if we did nitrogen and ammonium, so X plus 4 times +1 equals 1, charge of 1, so X is in a -3 state in this case. Now on the other end of this crystal, we have nitrogen in nitrate, which is X plus 3 times -2, and the charge is -1. So when we get done, we're going to find out X is in the +5 state. So the fact that we have nitrogen in a -3 state and nitrogen in a +5 state is what makes ammonium nitrate kind of a dangerous molecule, because the electron transfer could happen. But that's the algebraic method of calculating oxidation numbers.